Good morning. So, how are things going on? I will wait for a minute. See that there are only about 44 students there. Okay, I think let's get started. So we're looking at the design of this floating point adder subtractor circuit. It turns out that this is the most complex circuit that we'll be discussing in this course. All of the circuits that we'll be discussing later also will be simpler than this. Okay, let's not get scared of it. Basically, what we are doing is coming up with the design of each of the modules to implement the different steps in performing the floating point addition subtraction operation. Just to make you recall, the four major steps are the comparison of the exponents and determining which of the exponents is greater. Then doing the Mantis alignment that involves shifting the matrix of the number with the smaller exponent by the number of bits equal to the absolute difference between the exponents. Then we need to perform the addition or subtraction that is decided by the four entities, whether xe is greater than ye or not, and the signs of the two operands, and the control signal. I have changed it to AS just to make the things notation simpler. So if this AS bit is 0, then we want to perform the addition. If it is 1, we want to perform the subtraction operation. As you'll be seeing, whether the matrices are to be added or subtracted, right, is determined by all these four entities. And once we do the matrix addition or subtraction, the result of that may not be in the normalized form, and we need to perform the result normalization, which means that we need to shift the position of the binary point accordingly and adjust the exponent. And before the adjustment, the exponent of the result will be the greater exponent. If xe is greater than ye, then the results exponent will be xe, otherwise it will be ye, but there will be some adjustment of that in order to perform the normalization. So what we are looking at in the last class are the details of the different modules. Okay, so the circuit itself takes these two operands, x and y, which are 32-bit operands in the floating point standard format, and it will also take this control signal AS, indicating whether we want to add the two operands or we want to subtract y from x. Okay, and the result also has to be in the floating point format. And first thing that we need to do is compare the two exponents and determine which of them is larger exponent, and also we need the absolute difference between the exponents, because that is the number of bits by which we have to shift the matrix of the number with the smaller exponent. So yesterday in the class we have seen we'll have two subtractors acting in parallel, but the two subtractors get the two exponents in the different orders, right? The first subtractor subtracts ye from xe, whereas in the second subtractor we are subtracting xe from ye. So we get the difference, and then we choose one of these depending on the status of this xe less than ye signal, which will be indicating whether xe is greater than ye or not. If this is 0, then it indicates that xe is greater than ye. Otherwise, xe is less than ye. And that's actually related to the borrow bit B8 into the most significant bit of the subtraction operation, which is built using the 4-bit borrow look ahead subtractors, similar to the carry look ahead based adders. So if we call this absolute difference between the exponents as k, right, we'll be making use of this k to perform the Mantis alignment. And the Mantis alignment involves taking the matrix of the operand with the smaller exponent and shifting it by these k bits. So one of these matrices of the operands will go without any shifting, and that's decided by again this xe less than ye. And if it is 0, then 1 point xm will be passed on as input to the matrix adder subtractor. Otherwise, the 1 point ym will go as input to the 24-bit adder subtractor. And the smaller exponents mantissa will need to be shifted. So that's what we select in the second case, or in the second multiplexer. Please note that the order of the inputs here is different from the order of the inputs in the other multiplexer. So here 1 point ym and 1 point xm with the corresponding input 0 and 1. If x is greater than ye, right, then ym will be the matrix of the operand with this exponent. That's what we are going to shift, but we need to take into consideration the hidden one also. So what you are going to perform the shifting is on the 24-bit entity. And in the last class, we have seen how we can perform this shift operation by using the multiplexer, which we call it as the Mantis shifter, also the barrel shifter, right? And the naive way of designing this barrel shifter is to use a 24-bit 2 to 6 to 1 multiplexer, but that turns out to be very huge multiplexer, and that can be replaced with a smaller multiplexers. All right, noting that beyond the value of k32, the shifted value will be all zeros, right? So we take that factor into consideration, and now we perform this shift operation for less than 32 bits, right, by using the lower order bits of the k, right? And then we use this multiplexer based barrel shifter, which is a 24-bit 32-1 multiplexer. And the other case where k is greater than or equal to 32, the shifted mantissa will be all zeros, and that's what we are giving as input here. So the multiplexer will have these two inputs. Sorry for this. Let me just. So if the select bit is 1, then we are going to shift only. We are going to have only all zeros as the output of this multiplexer. Otherwise, whatever is the shifted mantissa is going to be made available. And what is the select line? It is the OR operation on the K7, K6, K5. When any one of these bits is 1, that indicates that the K value is greater than or equal to 32, right? And in that case, the shifted mantissa will be all zeros. Okay. So this is the circuit for the mantissa shifter, which we are calling it as the single block, and that's what is put here, right? And that gives us the shifted mantissa, which is aligned with the other mantissa. Then the next operation that we need to do is perform the addition or subtraction of these mantissas, right? And for that we need an indication whether we need to add the mantissas or the subtraction of the mantissas. That is decided by the 4 entities that we said, right? Whether x is greater than y or not, right? And the signs of the 2 operands, and the operation to be performed on the operands, whether it's addition or subtraction. and all these four will decide the sign of the result and also whether the matrices are to be added or subtracted. Okay, and this we have discussed earlier, and let me just go to the truth table for this ZS and MES generator. Okay, yeah, before I go to that, are there any questions? Yeah, we need to understand the operations, and then of course we need to understand how to design the circuit to perform each of the operations. Okay, and what we need to pay attention to know in this discussion is the kind of finer details that we need to take care, because even if the result is wrong by 1 bit, right, that can be I mean, that's simply not acceptable, right? So we need to make sure that the result is always correctly produced. Okay, yeah. Are there any questions about what we discussed so far? Okay. Yeah, now let's see how do we decide the sign of the result and also whether matrices are to be added or subtracted. So I have this truth table here where the input variables are the relationship between the XE and YE and the signs of the two operands and the operation to be carried out on the operands, right? Now, the first 8 rows here will correspond to the case where XE is greater than YE. I'm giving the truth table for these cases. I will leave it as an exercise for you to come up with the remaining part of the truth table. Okay. Now, if I take this combination of all zeros, what does that indicate? XE is greater than YE and X and Y are both positive, and I want to perform the addition operation. Right? So when we perform addition operation on two operands which are positive, the result will also be positive. That's why the ZS is 0. And because both are positive and we want to perform the add operation, the matrices have to be added. That's why the MES bit is 0. So that's a very straightforward case. The second case is X is greater than YE and both X and YS are positive, and I want to perform the subtraction operation. That is, I want to get Z equal to X minus Y. So again, because X is greater than YE, right, the sign of the result will be same as the greater than exponent. So that's why it is 0. And in this case, I want to perform subtraction operation on the positive operands. So the matrices need to be subtracted. That's why MES bit is equal to 1. And the next case is X is greater than YE, X is positive, Y is negative. Then I want to add these two numbers, right? That's what is indicated by S0. And because these operands are of opposite sign and X is greater than Y, right? The sign of the result will be 0. And because the operands are of opposite sign, we need to subtract the matrices. That's why this MES bit is 1. So this is the logic that we need to use, right? So we can quickly verify the other entries here. And X is greater than YE, X is positive, Y is negative, and I want to subtract Y from X. And because Y is negative, right, and I want to perform the subtraction operation on Y, it requires addition of the matrices. And because X is greater than Y, the results sign will also be positive. That's why ZS is 0 and MES is 0. Then the next 4 cases are basically X is greater than YE and X is negative, right? And if X is negative and Y is positive, and if I want to add these two numbers, right, because X is greater than Y, the sign of Z will be same as sign of X, so that's negative. And because the operands are of opposite sign, I want to add them, we need to subtract the matrices. Okay. So this is the logic that we need to use to come up with the entries for truth table. I leave it as an exercise for you to verify the other entries here, right? And also, I'm leaving the blanks here for the rest of the truth table, right? Please fill that truth table. And final expressions I'm giving you here, okay, where we'll have one expression for the sign of the Z and one expression for the mantis add subtract signal. All of these are functions of these 4 inputs, and these are the min-term expressions, as you can verify, right? The ZS right, has all these 4 ones here in the first half of the truth table. So they are 4, 5, 6, 7. The rest of things I'm giving here, but you can fill the truth table and then verify that. And similarly for the MAS signal, you can verify that we have one here, and one here. That is 1, 2, then 4 and 7, right? That's what you have as the midterm expression here, right? And then when we use the corner map, right, we can get the Boolean expression for the sign of the result and also for the Mantis addition subtraction signal. It turns out that Mantis addition subtraction signal is nothing but the exclusive OR operation on the signs of the two operands and the add or subtract signal. Okay, whereas here the ZS will be dependent on the XE less than YE bit, right, and then the signs of the two operands, right, and the add or subtract signal. So this is the minimal expression for the sign of the result. And we can realize this using a two-level logic gate, and that's what will be going in as the circuit in this module, right, which is called as the ZS and MAS generator, right? So basically there will be two-level logic gate circuits, right, which will take these 4 inputs and then generate these 2 outputs, right? And one of these outputs, MAS, will go as input to the Mantis adder subtractor. And if it is 0, it will add the 2 Mantisas which are aligned. If it is 1, it will subtract the second Mantisa from the first Mantisa. And then it will produce the result of this Mantis addition subtraction. Let's call it as some SM, okay? And when you add the two 24-bit entities, the result can be 25-bit entities because there can be a carry out of the most significant bit. Okay, so it's possible that the output here can be 25 bits. Okay, now once you get this 25-bit entity, right, if I denote the bits of this SM as SM0, SM1, SM2, so on, SM4, sorry, SM. So total there are 25 bits, right? I'm calling them as SM0, SM1, SM2, and SM24. Okay, where is the binary point here? Because we are passing on 24-bit mantisas with 1 point something for the one mantisa, and the other one is shifted, right? The implicit binary point is between SM1 and SM2. Now, these SM bits can be in the normalized form or it may not be in the normalized form, right? And now we need to do the normalization, which means that I have to shift this binary point to the left by 1 bit, or I may have to shift to the right by some number of bits until where we have the first one in the bit sequence here starting from the left, because the normalization should result in a bit sequence where there is a single one to the left of the binary point. Actually, this we have seen with some examples earlier in one of the previous classes. Yeah, we've seen the case where we have taken this x and y, and then when we perform the addition operation, we have seen that it's, the result is 1 0 point, all zeros. So we have this 25-bit entities here. Now, in order to get the normalization, we have to shift the binary point to the left by 1 bit and increase the exponent. And other cases that we looked at is when we perform the x minus y, right? The result is not in the normalized form, and in order to get the normalized form, right, we need to shift the binary point to the right by 1 bit in the first case and by 3 bits in the second case, and accordingly the exponent is adjusted. And this has to be done automatically from the output of this mantisa, right? And that requires the detection of where the first one is present in the bits, and accordingly we need to shift the binary point, and we also have to get the shifted bit sequence that will correspond to the mantisa of the result. Okay, so now let's see how to design this part. Okay, and what is the first thing that we need to do? Given this 25-bit sequence, I need to find out where the first one is present. It's equivalent to saying how many leading zeros are there in the bit sequence. So what are the different possibilities? So let's say I have 1 in the SM0, then SM1, so on, SM24, right? Now, if this is 1, then irrespective of what the other bits are, right? This is the position of the first one. What is the number of leading zeros here? Number of leading zeros is 0 because there are no zeros before the first one, right? Suppose the result of this matrix addition subtraction is 0, 1, x6, so on, right? Where is the first one in this sequence? It is in the position SM1, right? And how many leading zeros are there? There is one leading zero, right? So the number of leading zeros indicates the position of the first one among these bits SM0 to SM24, right? Suppose I take the next one, right? So this corresponds to SM2, right? So now we see that the first one is in the position SM2, right? That is the bit 2 of the SM, and it also is equivalently indicated by the number of leading zeros here. That is, there are 2 zeros here, right? So now I want to come up with a circuit which will take this bit sequence SM0 to SM24 and then gives me the number of leading zeros, because once I get the number of leading zeros, that indicates where the first one is available. And once I get that information, then I know by how many bits I need to shift the binary point and how to adjust the exponents. Okay, yeah. So now what we need is a circuit to perform this operation of detection of the number of leading zeros. And because there are 25-bit positions, the output of this leading zeros detector, if I call it as D, right, which is the number of leading zeros, and also which gives the position of the first one, that's going to be a 5-bit entity. Okay, so now I want a circuit which will take this 25-bit entity as the input and then gives me this 5-bit entity as the output. Okay, so again, I'm giving the truth table here for this first few rows, right? So if it's 1 followed by all x, then the D value will be all zeros because that is the position 0. If it is 0, 1 followed by all x, x means it can take either 0 or 1, right? It's a basically don't care term, right? I mean, books use either x or D, right? So I don't want to use D here because D is already used here. And of course, x is also a bit of the operand. Let's not get confused with that. Okay. So here, the D value is 1. So that's given by this bit combination for the bits D4 to D0, right? And also we need to take into consideration what will be the ZM. That is, how do I get the 23 bits for this matrix? So please remember that this ZM is going to be only 23 bits because this is the matrix of fraction of the result. So if the number of leading zeros is 0, the binary point initially is here. Now I need to shift the binary point to the left by 1 bit. So what will be the matrix of fraction now? If the bit position is going to be shifted here, right? So the matrix of fraction for ZM is going to be SM1, SM2, so on, 23 bits. That is up to SM23. If it is 0, 1, then already the binary point is in the right position, right? Then we don't have to shift, right? And what will be the matrix of bits? It's SM2, SM3, and so on, 23 bits. So it will be from SM2 to SM24. If the number of leading zeros, sorry, if number of leading zeros is 2, right, then the binary point has to be shifted here, right? And in that case, the matrix of bits will be SM3 to SM24. That's only 22 bits. Then we have to put a 0 in the last bit position, right? And this continues. Let's say if the leading zeros is 23 and the first one is in the position SM24, right? Then the number of leading zeros is 24, right? That's what is indicated by this D value. Then the shifted matrix is going to be all zeros. Okay. And when I say shifted matrix, right, I'm talking about after doing the normalization, the matrix bits will be all zeros. Okay. So this is what needs to be generated by taking this SMS input and then taking the D value also into consideration. But first we'll look at how to generate this D value itself. Okay. So if you look at this truth table, this is a very familiar circuit for you. All right. We have seen this kind of a circuit earlier in the beginning of the course, right? Where the inputs are all 1 followed by don't care terms, or 0, 1 followed by don't care terms, and so on, right? Then the output is going to be indication of where the first one is, right? What is this circuit? All of you have implemented it also.
Priority encoder.
Sorry? Yeah, what did you say?
Priority encoder.
Priority encoder. Okay, very good. Right? So what all we need to do is simply use a priority encoder. Right? And the priority encoder is going to have 25 bits inputs, right? And 5 bits as the output. Right? So now we can see the purpose of the priority encoder was something else, right? Which was typically used to find the device with the maximum priority which you want to transmit the data. But here, noting that the functionality of the leading zero detector is the same as the functionality of the priority encoder, right? We implement this leading zeros detector as the priority encoder, right? And that gives us only the D value, right? Once we get the D value, I have to take this SMS input and then perform again the shift operation to get the ZM, and this ZM will be only 23 bits, right? And this will be something similar to what we have seen earlier, which is called as the barrel shifter, right? Which was used in the Mantis alignment, right? Here we use the barrel shifter to get the 23 bits that will go into the Mantis fraction part of the result, that is the Z. Okay. So now what is it we are seeing? We have taken the output of the Mantis subtractor, then we found the number of leading zeros, or we found out the position of the first one, and then we are shifting the binary point accordingly, and then getting the Mantis fraction for the result. What is the other operation that we need to do when we do this normalization? Whenever we are shifting the binary point, we also have to adjust the exponent, right? So that is the next operation that we'll be doing. Yeah. Are there any questions about that? What have we discussed so far? So basically what we have discussed so far, I mean, in the class today, is once the result of the Mantis addition subtraction is available, right? How do you find the position of the leading first one in the result, and then determine how many number of leading zeros are there, and that indicates how many bits by which we have to shift, and then get the result Mantis fraction. Okay. Yeah. Now we see that we have to adjust the exponent. Which exponent has to be adjusted? If there is no adjustment to be done, let's say if the result that we have is in the normal form, right? Then what will be the value of ZE, that is the biased exponent of Z? It will be nothing but the maximum of the two exponents XE or Y, because the result is always associated with the number with the greater exponent. Okay. So now the GE is what we are calling it as the maximum of XE and YE. And what is the adjustment that we have to do here? Yeah. Now let's say if I have GE, right? I want you to tell me what is the ZE in terms of GE. Yeah. In the first case, we are shifting the binary point to the left by 1 bit. So what has to be done to this exponent? Whenever we shift the binary point to the left by 1 bit, we have to increase the exponent value, right? So the ZE will be GE plus 1. What about in the second case? Already the binary point is in the right position because we have 1 here to the left of the binary point. So it is in the normal form. In the third case, we are shifting the binary point to the right by 1 bit, which means that we have to adjust the exponent. That is, we have to take the greater exponent and then subtract 1, right? And for the next case, it will be GE minus 2 and so on. Yeah. What is the last case? Yeah. Here we have to shift the binary point by how many bits? 22 bits. All right. Sorry, 23 bits, because the binary point has to go to the extreme point. Yeah. Now, what is the D value here? D value is 0, 1, 2, so on, 23. Sorry, 24. Now, can we get a generic expression for ZD in terms of GE and D? So, if D is 0, ZD is GE plus 1. If D is 1, ZD is GE. If D is 2, right, ZD is GE minus 1 and so on. You can verify that it is nothing but GE plus 1 minus D. Suppose you have the GE, then you add 1 and then subtract the D value, right? You will get these expressions. So if D is 0, right, ZD is GE plus 1. If D is 1, right, ZD is GE. If D is 2, ZD equal to GE minus 1 and so on. In the final case, when D is 24, right, you will get ZD is equal to GE minus 23. So now we need to have some small circuit, right, which will take this greater exponent, then add 1 and then subtract this D value, right? And this is what is called the exponent generator circuit. Yeah, sorry about that. Yeah, I have it here. So first we need to get the GE, which is the greater exponent of X and Y. How do we get that? We take these two exponents X and Y, and then we use this bit, which indicates whether X is greater than Y or not, and take one of these as the GE, depending on whichever is larger. And then noting that we have to get ZD as GE plus 1 minus D, we don't have to wait until D is available to get this GE plus 1. So we'll add this, we'll add this 1 to GE, right? And then get what is called the GE plus 1, which is nothing but the sum of GE and 1, right? And once D is available, then we subtract this D from this GE plus 1, and that will give us ZD, which is nothing but GE plus 1 minus D. Okay. So basically, this is the exponent adjustment that we are doing, right, after we do the normalization of the result. Okay. And now we need to put all these modules together in a single circuit, right, in a single diagram, right, so that we can do the timing analysis. Okay. Are there any questions about this normalization, shifting, and then adjusting the exponent? Okay. Yeah, now just to avoid the time that's to be taken for drawing the full diagram, I already drawn it here. I hope it's still readable. Okay. Yeah. I have the complete diagram here where everything is put together. Okay. So the first part is to determine the absolute difference between the exponents. The second part here on the right side is doing the Mantis alignment and then get the aligned matrices. Then this small module here will generate this ZS and the MAS signals. Then we perform the MAS subtraction, right? And then we do the result normalization here on the right hand side, which involves the leading zeros detector and also shifting this result of the Mantis addition subtraction by the required number of bits to generate ZM, that is the Mantis subtraction for Z. And the left hand side here is the exponent adjustment circuit, right, which will find the greater exponent and then add 1 and then subtract D, which is the number of leading zeros, to get the ZD. And once we take the ZS output here from the ZS MAS generator, and then the ZD that's coming out here, and the ZM that's coming out from the barrel shifter here. We put all of them together to get the result Z, right? So basically, this is the circuit which will take the two operands X and Y in the floating point standard, and then it will produce the result Z again in the floating point standard. Okay. Yeah. Now I'm going to ask you to do the timing analysis of the circuit in order to see how much time this circuit will take to perform the floating point addition subtraction operation. Okay. I know that it will take a lot of time for you to draw the diagram on your paper, on your sheet of paper. Okay. But I want you to mark at least the times that's taken for each of the modules. Okay. I'll give you a few minutes and assume that the fan-in requirements are met wherever it's required to take the large number of inputs. We'll assume that the fan-in requirements are met. That will simplify the timing analysis. Okay. Yeah. Now I want you to tell me at what time the outputs of each of the modules in this circuit is going to be available. Okay, let me start. So all the inputs are available at 0 tau. Okay. Yeah, let's start with the first one here. Left-hand side. What will be the delay of the 8-bit subtractor that's implemented using the 4-bit bar-look-add subtraction? As I said, it's similar to the 8-bit adder using the 4-bit carry-look-add adder. All of you know the expression for that, right? It's 2n by L plus 2, right? Where L is the number of bits in the CLA. Similarly, here L is the number of bits in the bar-look-add subtractor, right? So the output of this subtractor is going to be available at 6 tau. So even this bit will be available at 6 tau. Actually, it will be available at 5 tau itself. Doesn't matter really. Okay. Yeah. What is the delay of the multiplexer? Again, all of you have implemented the multiplexer circuit. It's actually a simple 2 to 1 multiplexer. And we have seen that the number of bits in the multiplexer in the data lines will not change the delay of the multiplexer. Right? So again, you can verify that the delay of the multiplexer is only 2 tau, right? And this input is available at 5 tau. The data inputs are available at 6 tau, right? Once the data inputs are available, right? After 2 tau delay, this K will be available. Okay. Meanwhile, let's mark the outputs for the other parts of the circuit here. So here again, it says simple multiplexer. I mean, a 2 to 1 multiplexer, right? So this will be available at, yeah. When are the inputs available here to the multiplexer? The matrices are available at 0 tau, but this XC less than YE is available at only 5 tau, right? So the output of this multiplexer will be available at 7 tau because the delay of the multiplexer is 2 tau, okay? And this multiplexer output is also available at 7 tau, okay? And what is the barrel shifter here? It's a 24-bit 32-1 multiplexer, which will have 5 select lines. So assuming that the fan-in requirement is met, right, we take the delay of this multiplexer also as a 2 tau. If the fan-in is less than 5, then it will take more delay. Okay. Again, as I said, to simplify the timing analysis, right, let's assume that the fan-in requirements are met. So this is available at 9 tau. Right. And what time is the K available? K is available at 8 tau. Okay. Yeah. Actually, we need to take that into consideration. So this cannot be available at 9 tau. because only after select lines are available, right, we can have the output of this shifter, right? So this will be available at 10 tau, right? And though these k bits are available at 8 tau plus then 1 tau for the OR gate, right? So this is available at 9 tau. And because the input to this multiplexer is coming only at 10 tau, right? So the output of this multiplexer is going to be available at 12 tau. Okay. And the inputs to this ZS and MAS generator, right? The latest input is available at 5 tau here because all the other inputs are available at 0 tau. And the circuit for this ZS and MAS generator is a 2-level logic gate circuit, right? So this will be available at 9 tau. Sorry. Right? So this will be available at 7 tau. So now we see that the input to this Mantis adder subtractor, one input is available at 7 tau, the other input is available at 12 tau, and the control signal MAS is available at 7 tau. So we need to wait for the second operand also available here, that's available at 12 tau. Then it will take the delay of this 24-bit Mantis adder subtractor circuit, right? And what is the delay of this circuit? It's a 24-bit adder subtractor built using the 4-bit carry look ahead adder, right? Yeah. What is the delay of this circuit? I just want you to tell me what is the delay of this 24-bit Mantis adder subtractor circuit. Yeah. That's why you need to be familiar with how we build this adder subtractor circuit. So that's built using 24-bit adder with 4-bit CLAs. That is the assumption that we are making, right? And if you remember, we have 1 tau delay through the exclusive OR circuit, because depending on this MAS bit is 0 or 1, right? We have to perform the negation of the second operand, right? So that will take 1 tau, right? Then 2 into n by L. So n is 24 bits here, and L is 4 plus 2, right? So it will be 1 plus 12 plus 2, that is 15 tau. Okay. So now we have to add this 15 tau to the latest input that is available, right? That's available at 12 tau. So this SM will be available at 27 tau, right? Okay. Now let's go through the other part here. So this xc less than y is available at 5 tau, right? So this multiplexer output will be available at 7 tau, right? And delay of this adder is it's an 8-bit adder, right? So if I use the 4-bit CLAs, so it's 2 into 8 by 4 plus 2, right? So it's 6 tau, right? So this will be available at 13 tau. But what time is the D going to be available? The input to this leading zeros detector is available only at 27 tau. And what is the leading zeros detector? It's a priority encoder. And now the question is, what is the delay of the priority encoder? Okay. Actually, that can be a little bit involved to analyze the delay of the circuit, right? But assuming that we can implement it as a 2-level logic gate circuit, all right, then we take the delay of this leading zeros detector as only 2 tau, right? So that will indicate that this available is this output is available at 29 tau. But actually, when you implement it, right, it can be more than this. Actually, that's what you would have realized when you implemented the 8 to 3-bit priority encoder, right? It's a more complex circuit than the 4 to 2 bit priority encoder, right? So in practice, the delay of the circuit can be more than 2 tau, but we'll make the assumption that it's 2 tau just to simplify the timing analysis. Okay, so we see that the D is available at 29 tau here, right? And again, we have an 8-bit subtractor using the 4-bit BLS that is again having a delay of 6 tau here, right? So now the ZD is available at 35 tau, and this barrel shifter is again at 2 tau, right? So this will be available at 31 tau. Actually, now you see that the ZS is available at 7 tau, and the ZM is available at 31 tau, right? And ZD is available at 35 tau. The different parts, right, that will be assembled to generate the result will be available at different time instants. But we need to wait for all the inputs to be available. That's all the parts to be available to assemble them together and then produce the result Z. So the overall delay of the circuit is actually 35 tau, but in principle it can be when you implement the whole circuit, right, depending on the fan-ins of the gates that are used, right, and depending on how this leading zeros detector, which is basically a priority encoder, is implemented, right, the delay can be even more than this, right, but this will be the minimum delay 35 tau, right. So what is this time that we are talking about? 35 tau taken for performing the addition or subtraction operation on two real values which are represented using 32-bit floating point format, right? Just to see how slower is this operation, what is the 32-bit integer addition operation delay? Just to be fair to the comparison, let's say we use only 4-bit delay without the higher order propagate and generate terms, right? Then we know the delay of the circuit is right. I mean, if you want to add a subtractor, right, it will be +1, so it will be 19 tau. Right. So now compared to the 19 tau it takes to perform the addition subtraction on the integers, right, we see that the delay of this floating point adder is about 35 tau, which is more or less double the time it takes for the integer addition operation, right, and it can be even more than that, right, depending on the fan-in specifications of the gates and also depending on how this priority encoder is designed, right. So basically this indicates that the floating point addition subtraction operation is at least double the time it will take, right, for performing the operation in comparison to the integer addition subtraction operation on the same size of the operands, right. Of course, you can speed up both the circuits by going for the circuit with the higher order propagate and generate terms, right. In that case, this will be 10 tau. You can easily verify that 10 tau or 11 tau, right. Whereas the 24-bit Mantis addition subtraction also we can implement it using the 4-bit series with the higher order propagate and generate terms. In that case, the delay also will decrease slightly, right? But still, the order of the difference between the two circuits will be more or less similar, right? So basically, whole of this timing analysis indicates that, right, the floating point addition subtraction is taking more time than the integer addition subtraction, right? And that's not unexpected, right? And more importantly, though there are very large number of finer operations that we need to do, right, to implement the different steps, right, still the circuit for the floating point addition operation does not take significant time. That's what is a more important factor, right? And this is still kind of manageable in the clock periods of the current day process. Only thing is it may take more than one clock cycle to perform the operation, right? Depending on whatever is the clock frequency and whatever is the tau value. Okay, yeah. Are there any questions? Yeah, I know that this is a little bit involved circuit, as you said earlier in the class, right? And I'll upload the notes on the module and also on the Google Drive, right? So please go through this circuit, and if you have any questions, we can discuss that in the next class, right? But what I want to do before you come to the next class is remembering that the circuit that you have designed is for the case where XE is greater than YE, right? So I want you to design the 32-bit adder, subtractor, for the case where XE is equal to YE. Actually, it will turn out to be much simpler circuit than this. Okay. Then one more exercise I'm going to give you, and I will not do this in the class, right? What changes you have to make in the design of the adder subtractor circuit for the double precision floating point operands, that is the 64-bit operands. Again, I want to do it for the XC not equal to Y. Circuit is going to be similar, right? Only thing is the specifications of the modules in the circuit will be different, right? So I want to take it as an exercise to come up with the specification of the different modules in the circuit for the case of the double precision floating point addition subtraction. And I will also leave it as an exercise for you to do the timing analysis. I will not do it in the class, even in the next class, right? I will only briefly discuss this first exercise here, and then we'll go into the design of the floating point multiplier circuit. Okay, so please take these two exercises as the homework, right? And then come up with answers. You can verify your answers with the other friends, right? If both of you get the correct answer, and then there is no issue. But if you get different answers, if only one of them is correct, then you need to figure out who is correct. Okay, yeah. Are there any questions? Yeah, you can find the details of this topic in any book on computer organization by Hemashare or even the book by Stallings, right? They'll have all this discussion, right? Only thing is the timing analysis might not be there, right? But the details of circuit are available in these two books. Okay, yeah. Okay, maybe let's stop at this point. If you have any questions, so then I would like to take. Yeah, if there are no questions, maybe then we'll close the session now. Yeah, regarding the tutorial slot, okay, I think we'll discuss it next week. Actually, one of the civil engineering students, no, he has got a lab class in the P slot, so he doesn't want the tutorial in the P slot hours, right? So we need to find an alternative time slot. We'll do that because we'll not have any tutorial next week, so we'll decide on the tutorial slot later. Yeah. Okay. Okay. If there are no other questions, then we'll stop this session now.